We're surrounded by these perfectly engineered components, things optimized down to the micron. But what happens when these so-called perfect parts fail anyway? In this explainer, we're going to use the high-performance gears to see how an obsession with optimizing one tiny part can make us blind to the real reasons things go wrong.
Just take a look at this. This is a crown wheel gear, and it is a masterpiece of precision engineering. Components like this are the absolute beating heart of everything from your car's transmission to massive wind turbines. They have to be perfect, because in systems like those, failure, well, it just isn't an option.
So here's the big puzzle we're going to tackle. If you've got a gear that's machined perfectly, made from the best materials, what on earth could make it fail? The answer, it turns out, is hidden in the very last fiery step of its creation, the heat treatment.
Okay, to really get this, we have to look at the old-school ways of strengthening metal. For decades, the whole process has been as much an art as it was a science, and frankly, an art that was often defined by its flaws.
The main villain in this whole story is something called thermal stress. I want you to imagine plunging a red-hot piece of steel into a vat of cool oil. The outside skin cools and shrinks almost instantly, but the inside, it's still scorching hot and expanded. These two forces are literally waging a war against each other inside the metal, twisting and deforming it from the inside out.
And here's just how big of a problem that is. That internal battle, that thermal distortion, can be responsible for up to 45% of a product's final errors. Think about that for a second. Nearly half of a gear's precision can be completely wiped out in the very last step of making it.
So here's a classic technique. It's called induction hardening. You use these electromagnetic coils to heat the gear up. A high frequency just heats the very outer layer, while a lower frequency goes deeper. It's this really delicate dance of energy to get the hardness just right. But as you can imagine, it is incredibly difficult to control perfectly across a complex shape like a gear tube. So the bottom line is that these traditional methods are a constant struggle. They're expensive, they rely on a whole lot of trial and error, and the tiniest imperfections can lead to catastrophic failures down the road. It was pretty clear that a better way was needed. And that brings us to the hero of our story, or at least what seemed like the hero, artificial intelligence. AI promised to take all the guesswork out of heat treatment, kicking off a whole new era of digital precision.
And right away, the impact of AI was just stunning. While the old statistical models could predict failure with about, say, 91% accuracy, AI-powered neural networks shot up to nearly 99%. That is a massive, massive leap in predictive power. And this wasn't just on paper either. The AI-guided processes were producing physically better parts. Dimensional precision got a huge boost, jumping 2 full levels on the international quality standard. And by optimizing the steel's internal structure, fatigue resistance went up by as much as 30%. The gears weren't just more precise, they were a whole lot tougher. Then when you apply this AI approach to entire systems, the benefits just cascade. Machines ran longer between failures, unplanned downtime plummeted, and repairs got faster. On paper, AI was a total decisive victory.
But, and you knew there was a but coming, right? This is where the story takes a sharp turn. The numbers, they look incredible, but they mostly exist in a world of simulations. So the real question is, does this promise actually hold up in the real world?
Which leads us to ask the big question. Is AI really the magic bullet for manufacturing? Or is there something that the data isn't quite telling us?
And here it is, the fine print. When researchers really dug into these studies, they found that the huge majority of these amazing results came from computer simulations, not from physical tests. The few real-world experiments that were done used tiny sample sizes, sometimes as few as 2 gears. And there is a world of difference between a perfect result in a simulation and a reliable part out on the factory floor.
So here's the crucial point. AI didn't invent some new way to stop metal from warping. The fundamental physics of failure, they're exactly the same. AI is just exceptionally good at predicting and compensating for those old problems. It's treating the symptoms with incredible precision, but it's not actually curing the disease.
This realization forces us to stop looking at the final step and start asking a totally different question. What happened to this gear before it ever saw the inside of a furnace?
This quote from the research is really the key that unlocks the whole puzzle. Distortion isn't just about the heat treatment. It's about every single thing that came before it, the entire manufacturing history of that component.
Let me put it another way. A gear isn't some static object that you can just optimize in a vacuum. It is a physical record of its own creation. It carries the memory of every single process it has ever been through.
And that, right there, brings us to the real solution. It's not about finding the perfect algorithm for just one step in the process. It's about understanding the entire system. This really illustrates the hidden forces we're talking about. On the one hand, you see the gear's physical geometry. But next to it, you see something invisible, a map of its internal residual stresses. You can think of these as tension that's been locked deep inside the metal. These stresses were created long before heat treatment, and they're just as influential as the physical shape of the teeth.
So success or failure is really determined by a whole chain of events. It starts with the basic shape. Then you have the history of the metal itself. Tiny variations in its alloy mixture from when it was forged and rolled. After that come the stresses from the cutting and shaping process. That final heat treatment, it doesn't cause the distortion, it simply reveals the sum of all these hidden stresses that have been built up along the entire journey.
And this is our main takeaway. Focusing all of our advanced technology, like AI, on just one tiny part of the process, that component-level optimization, it's a losing game. True reliability, that comes from system-level reasoning. You have to understand the entire history of the part to get it right. And this all leaves us with a final, really critical question. As our tools get more and more powerful, allowing us to optimize the tiniest details with incredible precision, are we becoming so focused on the individual trees that we're forgetting we're standing in a forest? Are we remembering to see the whole picture?